All right, the third talk of the session is Frictio, passive kinesthetic force feedback for smart ring output, and we have a plethora of different collaborating institutions here, and Teng is going to give the talk.
Okay, good afternoon. My name is Teng. It's a pleasure to present our work, Frictio, passive kinesthetic force feedback for smart ring output. The work was done at Dartmouth College under the supervision of Professor Xing-Dong and with collaborations from Qian, Michelle Annett, Fraser Anderson, and Da-Yuan Huang. It is commonly known that the smart rings can be used for subtle, always available, and eye-free interactions. For example, in this meeting scenario, the user can rotate his ring to check his calendar without being noticed. The smart rings are mainly used for input purpose so far. The feedback of the using smart ring is still very limited. Current smart ring output mainly focused on the light, sound, vibration, skin drag or poking, thermal, but these all usually requires the substantial user's attention and are often decoupled from the input mechanism. Alternatively, we designed the Frictio, a smart ring device that uses a passive kinesthetic force feedback for users' rotational input. Smart ring has three major advantages. Frictio has three major advantages. First, it provides the force feedback to users in response to their input actions. Oh, I should play a video. Second, this form factor, this fits to the smart ring form factor very well. And lastly, different force profiles can be designed to enrich the interactions. I first clarify the terminologies we used. Haptic user interfaces encompass both tactile and kinesthetic for feedback. The tactile feedback relies on the continuous skin senses and is created by stimulating the mechanical receptors of the skins. The vibrotactiles from our smartphones or smart rings and the distributed forces as shown on the left figure are examples of tactile feedback. On the other hand, the kinesthetic feedback relates to the feeling sensed by the user's muscle, tendons, and joints. The right figure shows the example of the kinesthetic feedback. In that one, the user wants to move his finger to left where he feels the resistant force to the right. And people often differentiate active and passive haptic feedback from either the user's perspective or the device's perspective. In this work, we differentiate the active and the passive feedback from user's perspective. Frictio is an example of the passive force feedback. In this one, users want to rotate their ring while they feel a resistant force from the ring device. And now I would like to show you the design of the prototype of Frictio. This is the exploration diagram of our prototype. It consists of an inner race for fingers to wear, an outer race that is rotatable, 18 miniature magnets that are embedded in the outer race and are evenly placed 20 degrees apart from each other with alternating magnetic poles, and a brake pad that provides the friction force to the outer race, the motor and the rack that controls the position and the movement of the brake pad, and a proximity sensor that induces the position displacement of the brake pad, and the two Hall sensors that detect the magnetic field strengths to induce the rotational angles and directions. The Frictio prototype was 3D printed. As you can see on the finger, there is a brake pad that provides the friction force to the outer race, and the Hall sensor to detect the rotational direction and displacement. Here's a video showing the Frictio in action. The brake pad moves in response to user's rotational input, and the user feels the friction force feedback as a result. To explore the capabilities of Frictio, we designed 6 different force profiles. These force profiles were rendered over the rotational angle, time, or both. With no force, the outer race is free to rotate without any resistant force. The hard stop will prevent the user from rotating the ring, so it can be triggered after the user rotates certain degrees. With resistant force, the outer race is still rotatable, but it requires some extra force extra effort from the users. The friction provided by the brake pad increases with the ramp up, and the ramp down is opposite to ramp up. The outer race is progressively easier to rotate as users rotate the ring. The bump stops the outer race from rotation, but the user needs to spend an extra effort to overcome that. So I would like to show you several videos describing these force profiles in details. This is the no force. As you can see, the brake pad stays still, and there is no resistant force provided from the friction. This is the hard stop. The brake pad drops quickly at a certain angle, and it prevents the outer race from rotating. With the resistant force, the brake pad stays in contact with the outer race and provides a constant friction to the user. With the ramp up, the brake pad moves down slowly as the user rotates. And the ramp down is opposite to ramp up. The brake pad moves up as the user rotates the ring. With the bump, the brake pad drops quickly and provides a strong friction to the outer race, and the user needs to spend extra effort, strong effort to overcome that. With these force profiles, we designed 4 different applications to indicate how Frictio can be used for interactions. Checking the time is often inappropriate in many settings. This can be mitigated by using Frictio. For example, the ring is unmovable if the user is late to the meeting. Providing the rotational input usually requires the fine motor control or user's continuous visual attention. To mitigate this, we can provide the haptic landmarks by using the bump feedback. In this lock application, the users can unlock the device by providing a series of alternating rotations. The traditional game input can be mapped to this rotational nature of the device. In this game, the users rotate with the ramp up or ramp down force feedbacks to indicate the power and the direction of the slingshot. So receiving a call in the movie may disturb other viewers. Frictio can be used as an eye-free call display by using some predefined force profiles. So I just showed you a few interesting examples, but as a very new output modality for smart rings, there are still many questions that we don't understand. For example, whether users can perceive these force profiles very well, and whether the body motions and some mental workload can affect their perceptions. To explore this, we carried out a lab study that explores whether Frictio can be used as an effective output mechanism for smart rings. We had three independent variables. The first one was the force profiles as described before. And in the task, users will rotate the ring, and a random force profile will be rendered. And users need to tell as quickly as possible which force profile they just felt. So usually, like the body motion or hand motion may impact the user's perception for the force profiles. So we designed the walking and condition where users keep walking at 3 kilometers per hour on a treadmill while performing the task, and a standing condition where users stand stationary on the treadmill while performing the tasks. Besides mobility, we also introduced a secondary task to induce users' mental workload. The secondary task was designed from a modified stroke test to make sure that the secondary task was carried out simultaneously with the primary task. To know more details about the modified stroke test, you can refer to our paper, but to be short, the stroke test is like a color name is rendered using a random color, and the users need to figure out whether the color name and the color was a match. With the studies, I would like to point out several interesting findings from the studies. The first one, most force profiles can be easily distinguished even under conditions where users' physical or mental workload was high. The average profile recognition accuracy was 94% across all the users and all the conditions. This figure shows the recognition accuracy on the mobility condition and on the secondary task condition. The walking condition was labeled in the blue color, and the standing condition was labeled with the green color. The with secondary task was on the left. As you can see, the profile recognition accuracy was higher when the users were standing and when there was no secondary task. And this figure shows the average profile recognition accuracy across all the profiles we used. We found that hard stop was more accurate than the ramp down resistant force and the ramp up profile, but there was no significant effect found between other pairs. For the second finding, we found that physical workload didn't significantly impact the response time. The response time stands for the time elapsed from the beginning of the force profile to the time when the user pressed the space bar to tell which profile they just felt. In short, we didn't, for the physical workload, which means whether either the users were standing or walking, but there was no significant impact from this factor. For the third one, Frictio may not impact the performance of a second or parallel task. And this figure shows the accuracy of the secondary task across all the profiles. Although the hard stop, bump, no force have a higher accuracy than the others for the secondary task, but the average accuracy of the secondary task actually reached 94.1%, which is pretty high. So with the study result, I would like to send several take-home messages for this work. The first one, the different force profiles are easily to be distinguished, and they have different properties, so they can be used for different applications. For example, the bump and hard stops may be suitable for urgent messaging applications because they are easier to be distinguished. And second, we found that the resistant force is actually the major source for confusion with others, as its similarity to ramp up or ramp down. So for designers, if they want to use the ramp up or ramp down force profiles, it's better to avoid the resistant force. The last, Frictio could be useful for multitasking because from the studies, we didn't find that the secondary task, the accuracy was affected by using the Frictio as the primary task. So it's potentially be useful for multitasking. And for conclusion, we presented Frictio and proposed using passive kinesthetic force feedback as a variable or smartwatch output. And the different force profiles can be designed and be mapped to different applications. With this, I would like to thank my co-authors, and I'm happy to take questions. Thank you.
Hi, Chris Schmann, MIT Media Lab. So your mechanical design in that picture is very clever. I'm not convinced about the applications, but that's okay. But the size of that for something I would put on my hands is just huge. So if you were going to actually make something like this and try to get people to use them, you'd need the size to be about an order of magnitude smaller. So based on your user study, what would be the most essential functions that you would need to have in a ring like this?
So this is actually the size of the prototype is currently large for now. This is actually one of the biggest limitations of our work. So for the user studies, the device is small for the size of the user's finger, and the users mainly focus on detecting the which force profile they felt during rotating the ring without looking at it and without hearing any sound. So the center function will be which profile was that.
But what's the single most important thing that you can impart by this mechanical feedback?
Sorry, can you speak louder? I didn't.
What is the single most important sensation that you can impart through the mechanical feedback? I'm thinking about how to miniaturize this.
I think for this one, we mainly focus on providing the friction force to the user. So when they rotate the ring, they feel different frictions and different patterns from the frictions.
Okay, cool, because you could make that much smaller.
Thank you.
Let me just follow up with a question that is maybe an extension of Chris's question, and that is, as you miniaturize, some things will be easy to miniaturize and others will be harder. What do you think are the parameters that will be easy to keep as you miniaturize, and what will be harder to achieve?
So with our experiences of doing this project, we found that the motor part were actually very hard to miniature. But the brake pad, this part could be easy to miniature. But it's really hard to find a very, very miniature small motor that provides enough torque to rotate the ring. Thank you.